Our next chapter that we've been looking at are gases, which we've done a little bit of quick review of Regents level gas laws, which really revolves around the combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. And your homework, last week was kind of working with that equation and just substituting and solving. But there is another gas law equation that we'll be using in AP chemistry, which is what we would call the ideal gas law, which is PV is equal to nRT. P is pressure, just like it is in the combined gas law. V is volume. N is moles. R is a constant, which we'll come back to in a second. And T is temperature. Most of the same variables, really the two new ones are N being moles and R, which is our ideal gas constant. This formula can be found on your formula sheet, so you can look it up if needed, but most likely it's a formula you use often enough that you'll probably just know it. So going back to R, which is our constant, is the ideal gas constant. So what is it? R is equal to 0.08206 liters times atmospheres divided by moles times K. This is also on the formula sheet. So again, you don't need to memorize your gas constant. You can always look it up if necessary. The other thing to say about the ideal gas law before we kind of look at how it's actually used is to understand how this formula can be used to find the combined gas law. Combined gas law isn't given to you on the AP formula sheet, so you can either memorize it or you can understand how to figure it out from the ideal gas law. So if we take our ideal gas law and we put everything on the same side of the equation, so we would end up with PV and then we divide by nRT. This is what the ideal gas law would look like. The main difference between the ideal gas law and the combined gas law is the ideal gas law is looking at one single sample of gas, whereas this is looking at two. So if we take our gas law for the ideal gas law, now deal with two different samples of gas, my gas constant is a constant, so that's going to cancel out. If you look, what I have here and what I have for my combined gas law are pretty much the exact same. Now, you don't need to be able to do this, but if you don't know how to kind of rearrange this to get the combined gas law, then you need to just memorize this because you may need to use it on the AP exam. So how do we use the ideal gas law? Our formula is PV is equal to nRT. So we need to figure out what information we know. It tells us a sample of CaCO3 is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius. How many moles of gas were generated? So first thing we want to do is we want to set this up to solve for the variable we need to find, which is moles. So we need to get moles by themselves. So to do that, we divide by RT. We end up with N is equal to PV over RT. From here, now we just need to substitute in. So N is equal to, we have a 250 milliliter flask, which is going to be 0.250 liters. The one thing that you really need to pay attention to is you got to pay attention to the units in your constant. Your units have to match up. So if you don't have the same units as your constant, you need to change it. So I needed to convert milliliters to liters. The other information I'm given is pressure is 1.3 atmospheres. My temperature is 31 degrees Celsius, but this needs to be in Kelvin, so I need to convert. So I take 31 plus 273 gives me 304 K. And then my constant is 0.08206 liters atmospheres per mole K. From there, I need to just solve for N. If I pay attention to my units, atmospheres divided by atmospheres cancels. Liters divided by liters cancels. K divided by K cancels, leaving me with moles, which is exactly what I should get is my units on this answer. When I do the math, I get 0.013 moles. If we take a look at a second example, number 2 here, we're going to need to do the same thing. PV is equal to nRT. This time it tells us a scuba diver's tank contains 0.29 grams of O2 compressed into a volume of 2.3 liters. Calculate the pressure at 9 degrees Celsius. So this time we want to solve for P. So to solve for P, we need to divide by V. So you end up with P is equal to nRT over V. So now we want to start substituting in. We're solving for pressure. We know our volume is 2.3 liters. We know R is our constant. And we know 9 degrees Celsius is our temperature, which we need to convert to Kelvin, which would be 282 K. The number we don't know is moles, but what we do have is we do have information that we can use to get to moles. We know 1 mole of oxygen is equal to 32 grams. So we can convert kilograms of oxygen to grams and then grams to moles. 0.29 kilograms is 290 grams times 1 mole over 32 grams is equal to 9.0625 moles, which would have 2 significant figures. That's going to get substituted in here, so I end up with 9.0625 moles. Now I just need to solve for P. So 9.0625 times 0.08206 times 282 divided by 2.3 gives me 92 atmospheres is my answer, and I should be rounding to 2 significant figures. Again, my units cancel, moles divided by moles, K divided by K, liter divided by liter, leaving me with atmospheres. The last thing to do before kind of finishing this up is I want to give you a little bit of a clue on number 3, which you're going to kind of solve on your own in a minute. Same idea, PV is equal to nRT. We need to figure out which numbers do we know. It tells us that the sign contains a pressure of 1.78 torr. That's going to be our pressure. We would need to convert that to atmospheres. If you look earlier in the chapter, we do have a conversion factor for that. So 1 atmosphere is 760 torr, so you can convert that. Our temperature is 35 degrees Celsius. We can convert that to K. R is a constant, so we always know that. We want to solve for moles because we know that eventually we need to find grams of neon. If we know moles, we can get to grams. So the other quantity that we need is volume. They tell us volume is equal to pi r squared times height for a cylinder. We know the diameter and we know the length, so we can calculate our volume using that. Your units don't match up, so make sure you get to equivalent units, but beyond that, solve for volume, plug into your equation, and then you should be able to solve for moles.